welcome everyone. So this is a topic that's really generated a lot of interest in the RF and high-speed design communities. And so before I hand off to Hisu, I'd just like to kick off the presentation and set the context and talk a little bit about why we think this is such a hot area right now. So as you'll see later in the presentation, there's really a standard set of tools that RF designers are typically using to model and simulate packages and interconnects. There's the base RF design software, such as ADS from Agilent, and in that you get schematic and layout design environments. You get a wide range of system and circuit simulators. And then at that point, it's really up to the RF designer to provide the right set of models into these simulators. So these can be ideal models based on lumped element equivalent circuit models or SPICE models. They can be measurement-based models if that data is available for some of the components in the design. And then also EM models are becoming more and more important, especially as design frequencies are going higher, and also as higher levels of integration are pushing more components and traces closer together into smaller packages. So we'll talk about the advantages and the trade-offs of all of these model types in this presentation. I would like to take a minute to zoom in on EM models. To create EM models, a lot of companies have dedicated EM modeling engineers who are very experienced in using EM. But one challenge in using EM models has to do with how the RF design software interacts with EM software. So as an example, let's say that you want to model the interactions between a package and some traces on a PC board. So what you might do is export the PC board layout that's in the RF design software to the EM software where your 3D model of your package is. And that first step can take quite some time, can be a tedious process, maybe several manual steps to do that export. Once that's done, you can run an EM simulation and then export an S parameter file back to the RF design software. But this S parameter block may have dozens of ports, and to connect it back into the schematic and run circuit simulations, that can also be somewhat of a tricky process. And then if you want to make any changes to the board layout, you basically have to repeat that entire process. So you can see this is really kind of a static design approach and not real efficient. So because of these inefficiencies, we've seen the emergence of EM simulation tools directly integrated into the RF design software. So for example, in ADS, you can now run planar 3D EM simulations using momentum, as well as full 3D EM simulations using finite element technology. Now, this integrated EM certainly doesn't eliminate the need for standalone EM modeling tools, but there's some applications where integrated EM will be a lot easier, it'll save lots of time and really allow RF designers to move from a static design approach to a much more dynamic co-design approach. So the good news is that RF designers now have direct access to EM simulation technology in their design tools. But there is a caveat. Even though EM simulators have become more accessible and easier to use, it still takes some experience to generate an accurate EM model. So this is why I think that the topic of this paper has really generated a lot of interest. A good EM model really requires that we can accurately represent all aspects of the physical component that we're trying to model, whether it's a package, a connector, a set of interconnects, interconnects on ICs, interconnects on boards. And so one way to look at it is we have to make sure that the simulation environment matches the measurement environment. And it turns out there's many factors here. There's physical dimensions, there's material properties, and then there's even the manufacturing variation from sample to sample. All of these need to be taken into account to get an accurate EM model. So the latter part of this presentation will talk about these factors and how to best create EM models that accurately represent the physical world. So I've talked a lot about EM, but EM's really only part of the story, and Hisu will be covering several modeling approaches. So why don't we get started? So at this point, I'd like to introduce Hisu Lee, who will be showing us each of these various modeling approaches. And so, Hisu, I'll let you take it from here.
Thank you, Mark. Hello, everyone. Basically, this presentation, as Mark mentioned, we'll be talking about a lot of modeling aspects of the interconnect and package steps. However, at a higher level, there are basically two main objectives. One is basically we will be learning what are the different types of electrical motors and when and where to use. The other is to understand what really affects the accuracy of those motors. As we seen from the slide, this is one of the typical dot boards that comes with the packages and connectors and all different types of electrical circuits. From this picture, we can see a lot of different transitions and interconnects are used. For example, let's take out one of the connectors in this design. If we zoom into it, we're going to see the connector to the PCB trace launches. And also on this microchip traces, there is more of the discontinuities. And from the package side, here is the PCB trace to the package pad transitions. And top of it, there are multiple bond wires which are more of the interconnect used in this design. So transitions and discontinuities as well as the old parasitic can no longer be ignored in RF and microwave as well as the high-speed digital designs. Such smaller form factor and the higher frequency of the operation increases design challenges of the design. So that's what we will be focused on to talk about how we develop the different types of motors and what are the advantages and disadvantages of each motor during this presentation. So there are basically four types of motors, starting with the lump motor and measured data, as well as EM motors and broadband splice motors. These are four typical type of electrical motors available in the market space. We will be using this sample structure shown in this slide to talk about the measured data, EM motors, as well as broadband splice motors. So the structure of this one is basically a through line between these two connectors. And the other side of the board, there is actually QFN package. So we will be using this structure to talk about how we develop the motors for these two different types of structures. So let's start with the lump motors. Lump motors is basically schematic-based motors. It provides a pre-intuitive physical meanings. It has a long history and modeling walls. So basically from the package, you develop the topology of electrical motors that represent cross-couplings as well as the loss through the lead frames. Basically, you build up the schematic-based electrical motors. Afterwards, you get the either measured or simulated data. From this data, you try to extract all the parameters such as mutual capacitance and mutual inductance from the electrical circuit topology. This type of motor is really good for low frequency and narrow band applications. However, the complexity of the motor is increased with a higher number of pin counts. Therefore, it will be a little bit time consuming as well as takes quite a steps to extract the motors when number of pin counts are increased. In terms of the accuracy of the motor, specific to the lump passive motors, what are really affecting the accuracy of this motor is based on the a couple of different factors. First, since the motor is extracted from the either measured or simulated results, the accuracy of the motor will be depending on how accurate the measured or simulated data you will be based on to extract those parameters. Second of all, accuracy of the circuit motor that includes the topology of the motor and as well as the complexity will define the accuracy of motors. If you like to go with the very simple and very fast modeling approach with the lump passive, you can actually just model a lead frame as a single register with the probable inductor. Then all the parasitic behaviors and higher frequency of operations will be ignored. Therefore, in order to increase the accuracy of motors, you need to add yet more circuit component to the motor that eventually increase the complexity of the motor. Top of it, a number of ports and pins for packages that will affect the accuracy of motors. The reason is because when we deal with the multi-pins, there might be a lot of mutual couplings, such as mutual capacitance and inductance we need to model. Therefore, increasing the number of pin counts or port counts, that definitely will increase the uncertainty of the accuracy of motors. Let's move on to the second type of motor, which is measured data. And measured data motor is basically black box as primary motors, but typically the accuracy of the motor is pretty good. One of the issue with this type of measured data motor, it doesn't have intuitive physical meaning for the motors, not like a lump passive motor we talked about. Since it is just giving us a black box as parameters, we don't know how much of the inductance or capacitance coming from this motor. So that's basically one of the downside of this measured data motor. And in terms of number of ports, this motor can handle, it will be limited by the number of ports the instrument can measure up to. And also, if we go into the certain special structures, for example, we like to measure a certain structures inside of the PCB or inside of the IC stack-up, and will be very, very hard to measure it since there are certain standard type of the ports configurations available for instruments. And the process itself is pretty tedious, and the setup of the measurement is pretty expensive. So these are the kind of things we need to consider when we go with the measured data motors. At the bottom plot, there are a couple of samples I plotted. So basically, this is one of the QFN input match measured data. The red and blue are the S11 and S22 data coming from both two 50-ohm terminations on the same package. So this shows us a kind of variations, even though we are measuring the similar circuits from the both ends of a measurement, still the results coming from the both S11 and S22 are not exactly the same, which tells us the kind of variations what we're going to see throughout this presentation. So what affects the measured data model's accuracy? First of all, we can think of the calibration. In order to measure something, we need to calibrate the instruments. Therefore, the first level of the variations coming in terms of the accuracies will be something around the calibration. As an example, what type of the calibration standards we are using for this measurement? Is that SOLT or is that TRL? That definitely will affect the accuracy of the motor data. And also, quality of the calibration standards will affect the accuracy of this, the measured data motor as well. And top of it, the important factors we really need to understand is, as I mentioned from the previous slide, I was measuring exactly the same structure for S11 and S22, which is placed on the both ends of the QFN package, but we see the different kind of results, even though the circuits are the same. So this is basically coming from fabrication or assembly tolerances and repeatability issues. Board to board or connector to connector, bond wires to bond wires, all the other connections are varied based on how we fabricate or assemble. So based on those differences or variations coming in, we're going to get the different type of results. And also, it is important to have a skilled measurement engineers to measure those type of stuff, especially when we are going up to higher frequencies. So from the bottom of this slide, we see some X-rays or the kind of photos of the copper traces and the picture of the plated side grounds of the PCB. There are, we can imagine there will be quite a variation, such as over-etched or under-etched, and the cleanness of the plated side grounds. And what about this compound mold top of this QFN package? What about the bond wires, length of the bond wires, as well as how much of this bond wires are pushed down throughout this fabrication process? These will all affect the accuracy of motors. Speaking of those measurements, this is the kind of the additional slide to talk about different types of the calibration methodology from the sense, from the view of what about the accuracies, as well as how easy to go with those different type of calibrations. So as we can see, there are different types of the calibration, SOLT, which is using the standard short open load Thru, and there will be another type of calibration, such as TRL and LRM. Based on what type of calibration we are using, the accuracy will be changed, but at the expense of the complexity of the calibration process. And third motor we'll be talking about is basically EM motors. EM motors is similar to the measured data, which produce basically black box as parameter data. But one of the good things of the EM data is there isn't limitation on number of ports and structures. Wherever we want to measure, we can put the ports and measure it. And also, if we like to go with a 16 ports at a same time, we can set it up the simulation to go with the 16 ports. But when we think about measuring the 16 ports at the same time, there is no easy way to do that. So that is one of the benefits of EM motors compared to the measured data. And also this EM motors allows to easily model those fabrication or assembly tolerances with a parametric analysis for DFM or design centering by changing the certain parameters, such as material properties or the structure size of the structures. We can understand the variations pretty well, which is pretty hard to do that with the measured data. Additionally, versatile EM visualization provide us an additional benefit to visually inspect designs for performance enhancements. So one of the examples here, what we are seeing is basically E-fields distribution on the QFN 50-ohm termination structure. By looking at how fields are propagated throughout the structure, there might be a chance for designers to improve the quality of the design or improve the performance of the design. Speaking of the EM motors, there are various different types of EM simulation technologies available. For example, FDEM, finite element method, and FDTD, finite difference time domain EM simulation technologies, as well as we probably see MOM, method of moments simulation technologies. As you could see from this Venn diagram, there are certainly applications. Any of these technologies can be applied. However, when we go with the more of arbitrary 3D structures, we may not be able to use the MOM technologies for those type of structures. Just there are cases, each one of those technologies will have better fit compared to the other. So that's where we need to choose a different EM solvers to analyze the behavior of the structure properly. So as a summary, when you have more of the 3D planar structures, it will be better to go with the MOM technology, which is really specialized to analyze the planar structures. But when you have the arbitrary 3D bond wires, connectors, and type of interconnects coming in, then that's where you need to move to a more of the full-wave 3D EM solvers, which is more of the FEM and FDTD engines. Between these two, FEM and FDTD, FEM basically solves the problem, same problem, from the frequency domain perspective, whereas FDTD solves the problem from the time domain perspective. So FDTD type of the solvers will be really, really handy when you analyze any of behaviors of the structure from the time domain perspective. Whereas when you have the high Q type of structures, naturally FEM is fitting to those type of applications better than FDTD. So you need to choose a proper or adequate EM simulation technologies when you deal with those type of interconnects and package models. So what really affects the EM model's accuracy? First of all, material properties. We are giving a certain known values to the EM servers to get a known values out. So what are the known values we are providing the EM servers? One definitely will be a material properties, and the other will be the dimension of the geometries. And there are more, but those two are most important data we need to provide the solver to get accurate simulation results. So under the material properties, conductivity or dielectric constants, Low's tangents, roughness of the conductor, these are typical material properties we need to provide the solver to get accurate EM models. And top of that, accuracy of the 3D drawing models, this will be the important model we need to provide to the solver as well. If we put a different size of the dimension than what we measured, then we'll be getting the result different than what we measured. So here at the bottom, there is an example. This is basically the X-ray of the QFN package. If you look at the structure, bond wires may not be exactly the same to the one we see from the left-hand side, a picture. So based on the different lot numbers or samples, we may have a little bit of different size of the structures. So that's what we need to understand. What exactly we are simulating against what dimensions and what material properties are given to the structure. And in addition to material properties as well as the 3D dimensions we enter to the solver, they're definitely one of the factors that affects the accuracy of the simulation will be simulation accuracy that includes solvers, basis functions, and delta S, which is the convergence criteria of the simulator, and so on and so on. Well, for example, let's talk about the basis function. There are different basis functions in EM solvers, such as linear basis or quadratic basis. That's the way how we represent the fields around the cell cells. If we go with the linear basis, it will make the problem size smaller, but at the expense of the little bit of less accurate simulation results. If we can go with the quadratic by representing the more terms to solve the problem, but in the case, it will take longer to get the accurate simulation results compared to the linear basis. So based on what basis function we are selecting, we're going to get the different results. That will be another kind of factor that affects the simulation accuracy as well. So let's take a look. One of the example for EM models, since we are talking about the EM models in this presentation. Here's a very simple structure we simulated, but it sounds simple, but actually the structure itself is pretty complex from the EM or measurement perspective. It is basically 1 inch long, simple 50 ohm transmission line. The stack up is basically coming from a Rogers 4350 PC board that comes with the electric constant of 3.66 and Lowe's tangent is about 0.0037. These values are the values I basically got from the manufacturers, their web page. And to both ends of this PCB, there are 2 connectors. This connector is basically a southwest connector with a 2.4 millimeter the pin size. So we are measuring basically this connector, 50 ohm connector, this structure. And also we put exactly the structure into a EMPro, which is the 3D EM server from Agilent. So the structure what we are looking at here is very similar to the one what we're going to measure. But interestingly enough, if we look at this connector portion, we have the body of the connector, but we don't have the SMA connector to this drawing. So there was basically the reason why we weren't able to put the connector is because this is considered one of the IP from the southwest. So there was no easy way to get the 3D models of this SMA connector. So therefore, in EM models, we were missing this connector. So we were basically simulating this structure from this body of SMA connector through the 50 ohm to the other end of the body of SMA connectors. So this slide shows basically measured data for this Thru line. There are various samples we measured. So basically, what I'm trying to say here, these traces are multiple traces coming from the multiple measurements of same design but different samples. So as you could see, it's quite interesting. Even though we are measuring the same stuff, but the data coming from those measurements are not the same. So that means there are variations coming from all different regions. Could be a sample differences or fabrication tolerances, materials different, or over-etched copper or under-etched copper. So basically produce a lot of variations to the measured data, not only simulations, but measured data as well. From looking at this data itself, toward to the lower frequency, it pretty match up between the different samples, pretty okay. But as going up to the higher frequencies, we see the more variations. It depends on how you measure it. What are the samples? How the connectors are launched? And what about the cleanness of plated side grounds that touched up to the connector body, and so on and so on. So what we did, we tried to understand what are the variations or factors to this measured data. So one thing from this picture, what you clearly see that this is the side view of the PCB. There are bumps from the plated side grounds, which try to provide a better ground contact to the connector from the PCB. If you don't clean up this type of side bumps, then there might not, we may not have perfect contact of the connector body to the PCB. So that's something that always comes with those manufacturing, which makes a variation to the measured data as well. And top of that, when we look at the PCB copper trace, we try to maintain those etching within the certain the value or level, but there always there always be a more of the over-etched and under-etched. Therefore, we may not be having the exactly a 50 ohm as we wanted to have in the design. So these are the another factors. And from the bottom of these pictures, this is actually X-ray of the QFN package. This black area is basically solder, which is connecting the dipedal of this package to the PCB grounds. Like this case, for wetting, that provided a little bit less a ground contact for the dipedal of this package. Definitely, this will affect the accuracy of the measurement data. So that's why we saw that all the variations coming for those measure data are from the type of variations from a fabrication or assembly tolerances and variations. So what I try to do from this next slide, I try to build up a pretty similar kind of situation in EM data. So basically what that means, I try to change the dimension of the structure what we are simulating, such as let's put the other kind of gap between connector body to PCB plated side grounds, so that we represent those gaps to see the variations of the results. And also, instead of just making the complete open between connector body to plated side grounds, let's try to put the more of the point contact, which is similar to the bumps what we saw from the plated side grounds, so that it provides a certain level of the ground contact, not perfect, but we try to represent the structure as well. And also, if we look at the vendor's data for the connector, the top one for the pin is kind of recessed. So there is a little bit of gap for the edge of the Teflon to the body of the connector. We try to represent those variations as well. So by putting those variations into the design, what we saw, the result were quite varying from the simulation to simulation, which is similar to the measure data what we saw from the previous slide. So it will be very, very hard for everyone to just pick up one of the measure data, which could be the best one, and try to match up the simulation result to it. Will be very, very hard task. So we need to understand those natural variations coming to those measure data as well as simulation. We need to make sure what are the structures we are simulating that includes those material properties, whether it really represents the right value for the structure we measured. So I picked up one of the data from the simulation, and then I compared that data to all the measure data basically we took. So this black trace is coming from the EM, and other than this black trace are all measured data. So it shows you a very, very good agreements up to probably 20-something gig. It's picking up all the resonances properly. And moving up to the higher frequencies, as we saw the kind of variations in the measured data, it picks up the traces pretty well, but it's not just match it to the one of the data, which was the best case from the measurement that well. So there are certainly variations coming in. But generally speaking, from the top level understanding in terms of the comparison between the measured and simulation data, I say this result agrees very, very well between the two. So what were the basically factors on measured versus EM data differences? As we talked about, motors, which is drawn in EMPro, versus the one we measured, which is assembled, are the same. It may not, because there are a lot of variations coming in, as we talked about, such as connector to board gap and ground contact, cleanness of plated side grounds, and copper thickness. It could be over-etched or under-etched. Or top of it, the measured one, that includes the connectors. but the simulated one, it didn't include the connectors because of the IP issues. And in addition to it, what about the material properties? Those material properties we got from the vendor are accurate enough for higher frequencies, such as conductivity, dielectric constant, and loss tangents. So what we did, we tried to compare S21 data for that simple 50 ohm true line, the test case. So this black trace is basically the data coming from the EM simulation, and these traces, multiple traces, are basically measured data. If you look at the data, especially at the higher frequencies like 50 gig, the difference between measured versus simulated was about 1 dB. So that means EM models underestimated the loss. But the question came out for a accuracy of material properties for the conductors and dielectric, especially for the higher frequencies. I had a chance to talk to the person from Rogers, and what I got from them, the value what I was using for the simulation may not be correct data. They measured this under IPC standards, the regulations, but these are the values they can use up to a certainly lower frequency range, not going up to the frequency range. So what I try to do, I try to modify this material properties since these are not accurate values that represent a proper loss from the simulation, especially for higher frequencies. I try to come up with the modified values for the conductivity and the electric constants. As we all know, there are three important loss factors. One is the electric loss and conductor loss, and finally radiation loss. So I tried to modify this value, came with the value 3 to e to 7, and for the conductivity and loss tangent was about the 0.009. As you could see, with the modified value, it showed the better agreements from compared to the measured data. But still, there were around the 0.4 dB differences between these two. This actually 0.4 dB differences is coming from the missing SMA connector portion. So if we go back to the Southwest web page and try to find out the loss of the SMA connector itself, we could find their report saying that when they put the SMA, the body back to back, measured it, there is around the 0.4 dB loss coming at the frequency of the 50. So if we try to compensate those 0.4 dB loss, then we could match up this loss factor coming from the simulation to the measured data very, very well. Another interesting thing, when we talk about the loss, as I mentioned, there are three different loss, and going up to the higher frequencies, radiated loss will be increased. So this is the input power, and we plot the radiated power from the structure, which is the basically a simple QFN. As you could see from this picture, as the frequency goes up, radiated loss is definitely increased. So at the lower frequencies, the more of the important loss factors coming in will be a conductor and the electric. But as the frequency goes up, we need to consider the type of the radiated loss coming from the structure. Once again, with the EM visualization, you will be able to see this is the E field, and at the frequency of the 26, and this is the E field at the frequency of 50. So you see that a lot more the radiation is happening at higher frequencies. So this is the second example, what basically we tried. Instead of just having the 50 ohm through line, let's put the QFN package with the complex, the double bonding bond wires on this 50 ohm thin film circuit on gas substrates. Here's the data. These are all measured data again, and this black trace is coming from the EM. It follows the trend very, very well. However, there were a little bit of discrepancies, and we it's not picking up the resonances pretty well. I just realized that I made one of the mistakes when I did this EM simulation, but I wasn't able to put that result top of it. But generally speaking, this black trace of EM result is following the trend of the S11 from the measured data pretty well. So what are the factors here? As we talked about, these are all the variations, but specific to this example, running the simulation on the QFN and compared to the measured data, we don't know what exactly we simulated for the bond wires, especially for looking into this QFN package with the 50 ohm termination. What we measured may not be different than what we simulated. So this is one of the factor to that variation. And top of it, with this example, we have the compound molds. So by having these compound molds, we need to think about what are the material properties we are using for this compound mold as well. So these are the additional kind of factors that makes those variations in terms of comparing simulation data to the measured data as well. The last one is basically broadband splice motors, which is basically netlist-based circuit motor that includes the RLC and sources, and it should be the broadband performance. The motor generation process is very fast, and it also produces a different type of the motors, such as supporting the H-Spice or Spectre, Spice 2 and 3, and even it generates the motors for ADS. So from this point, I'd like to switch over and just show you how exactly the motors are developed. So let me bring up my window and show you basically ADS window. So let me open up here this ADS design, and from this design, basically what you could see is there is a tool menu, and you could see a spice motor generator. There are two options basically. One starting with the broadband, and there is narrowband generator. But in this case, we're going to use the broadband generator. So when I bring this up, it shows a pretty simple UI. Basically, what you needed to do is, since this broadband spice motor generator generates the motors based on the either measured or simulated results, you need to pick up what data you will be using as an input. So you go with the data set here, or you could go with the CD file or touchstone data. If you come with some kind of measured data, you can choose the touchstone. In this case, I'll be using the data set. And I can go and then browse it, and I'll be picking up one of the data I got, which was the EM simulation results coming from the QFN package with a 50 ohm termination, and open it. Then you will be able to specify what type of the netlist you would like to generate. So I'll just go with the ADS, H-Spice, Spectre, Spice 3 motors, and you can put the prefix to this netlist you're going to generate. For example, I'll just put in the MWJ, and afterwards you just go and then click this motor generation button. Then you start to generate the motors, and the motor generation is basically finished. And as you can see from this ADS trace, the red one is basically input data, and this blue one is basically motors. So the quality of the motors generated from this process is really, really good. As long as you have good data, you'll be able to generate the broadband spice motors in a second. So it's not only match a magnitudes of the data, but also look at the phase response. It is matched almost perfectly between the input data to the this motor data. And in terms of the output data, yeah, it definitely shows the results. However, if I bring up the ADS folder, under the ADS networks directory, it produces a networks. So if you'd like to go and then check it, I'd like to see the HSpice models, then you can bring up and see the net list generated coming from the dev process. It's very straightforward and simple to do. Since I am showing it on my desktop, let me just quickly show you what are the structure I simulated. This was the structure I talked about, basically having the connector, but not having the SMA portion. Here, there is a PCB. At the end of the PCB, basically, here are bond wires, and this green color is basically a 100 ohm thin film resistor. By having the two of them parallelized, we can have the 50 ohm termination. This is the way we are able to understand the transitional performance of this type of structures in the design. So if I bring up the one of the visualization data, I picked up the 65 gig. As you could see, there is quite a E field radiating from these traces. Not only kept those E field within the copper to the ground plane, there is quite a radiations coming out from it. Since this is the field data at the frequency of the 65. And also the other thing I'd like to mention, the complex of the meshes. This is very, very complex designs, not only from the size of the design, but also having the very small size of the bond wire, pretty big size of the connectors combined together. It always makes the EM solvers challenged, but it was solved pretty well. So let me go back to the presentation. So as I just demonstrated, broadband spice motors are basically netlist based, and the motor generation process is very, very fast, and it produces a very different type of formats. So you can actually easily share this netlist with the other colleagues or the other vendors you like to work with. But in terms of the factors on the accuracies on this broadband spice motor, accuracy of the input data will affect the accuracy of this motor. And engines algorithm, that's another factor. But generally speaking, it produces really, really good motor, not only for the magnitude, but also excellent phase matches. As a summary, I tried to make up this kind of table so that we can see all the detail of the data for different type of motors. But as a highlights, in terms of the accuracies, measured data, EM, and broadband spice motors will be providing the best solution for it. But from the other end of the viewpoints, understanding the cost of that, EM will be providing the best motors at reasonable cost level. But when we go with the broadband spice motors, will be in terms of cost, will be very, very low. So, as a summary of this presentation, each of 4 types of package and interconnect motors, it has its own strengths and weaknesses. The accuracy of motors basically depends on the various factors such as material properties and fabrication assembly tolerances. So we need to understand these factors, not only trying to match up the one EM data to the measured data. That will be very, very difficult. But eventually, understanding the corner cases, worst case, or even statistical models may be required for package and interconnect to take into account those variations. This might be the kind of ultimate goal for developing the models for packages and interconnects. EM and broadband spice motors offer the most economical solution from the accuracy and cost perspective. So as long as you have the engines rounds and you can use the EM to generate the motors, even you will be able to generate more of the parametric data, and then bring that data into broadband spice motor generator to generate the motors of it. And then you can exchange those motors with your team members and partners and that will be one of the most easiest way to exchange the design information between different teams and partners. Okay, that ends my presentation. So let me switch over to the Q&A.
Thank you, Sue. Okay, in a moment, we're going to rush on to QA in a moment. Remember to please complete the survey that will automatically launch at the end of the webcast. Any inputs that you provide, this helps us on how we can offer you more and better webcasts in the future. So please take a moment to do that. Okay, so reminder, you can set all your questions to panelists. And again, if we don't get to them live, we'll respond to them via email. So Mark will read out the questions. Go ahead, Mark.
Great. Thanks. Yeah, there were some good questions that came in during the presentation. I see more coming in now. So, Hisu, there's a question here from Mahmoud about what instruments were used to make the 60 gigahertz measurements.
Basically, I used the PNA.
So it's a high-frequency vector network analyzer.
Yes.
Is that right?
That is correct.
Okay. From Saqib, is there any way we can design circuits using shielded coplanar waveguide lines in the ADS environment?
I'm sorry, can you repeat the question?
Is there any way we can design circuits using shielded coplanar waveguide lines in the ADS environment?
Shielded coplanar waveguide lines. So from my understanding and my knowledge, actually, that can be done through the substrate stack-up definitions. Instead of making the top side as open, you can actually set the boundary conditions to the closed boundary that will be representing top side and bottom side closed. And then you'll be able to just create those coplanar structures and simulate it.
Okay, great. From Mohit, how did you determine the correct conductivity and loss tangent values in order to get the S21 results of the through line to match up?
Yeah, that's really good question. The differences I talked about between the S21 results between the measured and modeled, it may coming from a lot of different factors, not only the conductivity and loss tangent, but also a roughness of the structures. But when I ran the simulation, I didn't turn on the roughness for the simulator. So the way I did it, there could be a lot of different ways, but the way I did it, it was pretty simple for me. I went back to the ADS, and in ADS there is a line calc. And since this is a pretty simple 50 ohm transmission line, I was playing with the dielectric constants, loss tangents, and the conductivity parameters to get the certain level of the attenuation, which is basically I need the 1 dB more of loss to represent the correct behavior of the structure. And based on the that simple trier, I got the 3.0 and the 0.009 for the conductivity, the dielectric constants. And I use those numbers for the EM simulation, and then I, right the first time I got that result close to the measured data. But there might be some other way, but that was the simplest and easiest way to extract those modified or compensated values for the conductivity and low tangent.
Okay, great. Question from Mohammed. How can I model bumps in flip chip packaging?
There are very easy way, not only ADS but also EMPro. If you go with the ADS, there is the 3D component structures you can actually generate, which include the solder bumps. And in the EMPro, there is the macro, you can generate those solder bumps as well. So basically, you just produce those solder bumps and add the remaining structures and just go for the simulation. That would be the simplest way to do that.
Yeah, I should point out we do actually have an example design kit that has solder balls, solder bumps, and a few other 3D components that can be loaded into ADS and be simulated on FEM. So let's see, there's another question here. It seems like you only used finite element for the simulations. Is this the best simulator for analyzing packages?
Yeah, since the structure what we are dealing with are more of the frequency-based structures and models, so definitely FEM is the best kind of solution to model the packages and interconnects. However, you can use the FDTD technology to understand, especially the impedance profile of the structure throughout the interconnect what you are designing. So it will be nicer to combine those two technologies together to get all different type of results to understand the behavior of your interconnect and packages.
Okay, great. Did you consider the frequency dependence of epsilon? How did you modify the conductivity and the dielectric tangent?
I think we covered that question, right?
Okay, did you cover that in the demo already? All right. This goes back to the measurements, Sue. So you talked about calibration methods. A question from Scott is, which calibration method did you use for the 50 gigahertz measurements?
Basically we used the eCal, electrical calibration, to measure the structure of this QFN as well as the Thru line up to basically 65 gig.
Okay. There's a few more here. Let me just read through these. Okay, here's one from Song Lee. Does the EM cover the differential lines between I/O pins and the power plane? How is the EM compare to module compared to measured versus model for buses between layers? I'm not sure if I got that all correctly. Yeah. Do you understand that one, Hisu, or not? Maybe we can get back to Song Lee on that one.
Yep.
Okay.
So Mark, one thing I'd like to actually there was another question about how we broke the design of the sports and type of stuff.
Yeah, looks like we're running out of time here. So I do see quite a few more questions in the chat window. We do have everybody's email address. I think what we can do at this point is we can follow up directly on email and try to answer some of these other questions. All right, so Carmina, I'll hand it back to you.
Actually, Mark, I was just before we end, why don't we go ahead and get some closing comments from you if you want to share that next slide. Mm-hmm.
That'd be great. So thanks, everybody, for attending. We will be sending up a follow-up email with information on how you can get the slides from this presentation as well as some other material. You can see here on this last slide there's a link to where you can get all kinds of other material in Agilent EM solutions, including an overview of EMPro. We have brochures. We also have archived other webcasts. We've done several webcasts this year on the topic of EM simulation, so we'll have links to those archived webcasts if you're interested. We also have an EMPro workshop, which is a set of material that helps you learn how to use 3D EM, both frequency domain and time domain type tools, and that material is available. We also have some getting started videos that cover our various EM simulation technologies and how to get started in those tools. So once again, we will be sending an email out that has links to all of this information. Again, I'd like to thank everybody for attending our webinar, and we look forward to seeing you next month for our next in the series of innovations in EDA.
Thanks, Mark. Again, thank you very much, Hisu, for your presentation. And yes, thank you again for attending. We know your time is valuable, and we thank you for joining us for today's event, Accurate Modeling of Packages and Interconnects, brought to you by Agilent, ESOP, and Microwave Journal. If you're viewing the on-demand version of this webcast and have a question about any of the material, please email Hisu directly at he-sue Carmina_Lee@Agilent.com. The copyright of the presentation materials is owned by Agilent Technologies. For current schedule of live and on-demand events, I'm actually going to go ahead and send two links to gem stations in the chat window, and you can go ahead and use that URL to look at our recorded webcasts. I'm Carmina. Thank you for joining us, and have a great day.